Listening to my presentation on concrete architecture of Bitcoin Core. And here's our team members. What's in the report? In this report, we will analyze the concrete architecture used in Bitcoin Core and evaluate its effectiveness in meeting the needs of the network. We will examine the various factors that affect the durability and the reliability of the concrete in Bitcoin nodes, including environmental factors, structure design, and the maintenance requirements, by conducting a thorough analysis of the concrete architecture using Bitcoin. We hope to provide valuable insights into how to improve the durability and the longevity of this critical infrastructure. The reversion process, we analyze Bitcoin software in 3 stages. First, we improve scalability and reduce computation requirements by modifying this major scale to a client and server plus peer-to-peer architecture. This separation allows for more flexibility and resilience to change in the network environment. Next, we analyze the software's dependency relationships by reviewing its source code documentation. We gain a comprehensive view of the system's architecture and identify unexpected dependencies. Finally, we compare the concrete and conceptual graphic to gain insights and create a more complete understanding of Bitcoin's dependency relationships. This knowledge will guide further analysis, ensure it is continued growth and resilience. This is a conceptual architecture from Simon Wan, and this is the new architecture. In our previously research, we identified 8 subsystems for Bitcoin Core and consider its main architecture style as peer-to-peer and layer style. However, after examining the source code, we identified 2 new subsystems, API and RPC, and crypto, and replaced the layer style with the client-server style, modules, and different functionalities, and organized into horizontal layers, connect with layer style. For API and RPC, it provides developers with a way to interact with the system programmatically. This allows developers to build their own application and services on top of the Bitcoin Core without needing to implement all the functionality itself. For crypto, it provides the cryptographic primitives needed to secure the Bitcoin network, including encoding and decoding. This subsystem was previously considered a secondary subsystem under validation, but it's actually an important subsystem of Bitcoin Core as it offloads some of the burdens from the validation through the use of library functions and improves efficiency. We also renamed some of the subsystems and changed their functionality. For instance, blockchain was renamed to storage to reflect its broader function of storing information related to the Bitcoin network. Since we have 10 subsystems, we grouped them into 5 groups by their functionality: user-facing, developer-facing, blockchain operations, networking, and security. This is the concrete architecture we use to understand to research the dependency between subsystems. Based on this, the biggest discovery is that crypto is a special kind of subsystem that doesn't depend on anyone, but provides security for others. API and RPC are relied upon by all subsystems except crypto, and provide the required responses. There is also some interdependencies between API and RPC and storage. API and RPC and node networking and storage consist and validation. More detailed reflection on concrete. In the case of Bitcoin software, the analysis revealed several dependencies between subsystems that were not accounted for the conceptual architecture. For example, the UI subsystem depends on the validation consists mempool, many API and RPC, node networking, and crypto subsystem. The wallet subsystem has a direct dependency on the consensus subsystem, which was not shown in the conceptual architecture. The mining subsystem has the direct dependencies on the consensus subsystem, and the node networking subsystem. The storage subsystem has direct dependencies on the consensus subsystem. The validation subsystem depends on the mempool subsystem, and the API and RPC subsystem relies on the mempool consistent validation, nodes networking, and the storage subsystem. The node networking subsystem depends on the mempool subsystem and the constant subsystem.
In this section, we focus on the wallet as our second level subsystem for examination. When dealing with a new subsystem, the initial step involves creating a conceptual architecture. This can be achieved by revealing the available documentation, which aids in understanding the interactions among the wallet components. Subsequently, we analyze the wallet source code to establish the concrete architecture. The final stage entails in comparing the conceptual and concrete architectures using reflection analysis to identify any unexpected identities. As illustrated in Figure 2, the Bitcoin wallet system consists of 5 primary modules: transaction creation, key management, address management, transaction broadcasting, and transaction history. These modules work together to securely and efficiently process and manage transactions within the Bitcoin network. We begin by analyzing the key management and address management as the most crucial parts of the wallet architecture. We then delve into the source code to understand the dependencies within the subsystem and to obtain the concrete architecture of the wallet subsystem, as shown in Figure 3. Through our analysis, we discovered 3 new components: UTXO, management, backup recovery, and security and encryption. These components play a vital role in maintaining the integrity and security of the wallet while enabling smooth transaction processing. A reflection analysis was performed to understand the dependencies between these components. We found several essential dependencies such as the user interface relying on UTXO management, backup and recovery, and security and encryption. Furthermore, we identified dependencies using between UTXO management and address management, as well as transaction creation and UTXO management. Finally, we discovered a bidirectional dependency between backup and recovery and key management. In conclusion, our analysis of the wallet subsystem provides valuable insights into its architecture and within the Bitcoin network. The Bitcoin transaction process begins when the user starts the transaction using the UI by entering the recipient's address and the amount to send. The wallet software calculates transaction details and signs the transaction with the user's private key using cryptographic libraries. The signed transaction is broadcasted to the Bitcoin network via the API and RPC components. As the transaction moves through the network, the PD and CM component relays to other nodes, and the transaction is added to the mempool. Miners then select transaction for the next block. During mining, cryptographic libraries help find a valid proof of work solution. Once found, the new block is sent for validation, and if successful, the transaction is confirmed. The consensus algorithm updates the local blockchain and synchronizes with the other nodes, completing the process. In Bitcoin mining, miners interact with mining software using the UI. The API and RPC component discover peers and connected nodes in the network. The PD and CM component obtains the miner's wallet address and adds transaction to the mempool. The mining software requests the consensus algorithm to verify the transaction threshold and hashes transactions using cryptographic libraries. Transactions are added to a new block and validated. The process is illustrated until the block is approved. Once confirmed, the block is added to the blockchain and local copies are updated. Mining rewards are sent to miners' wallets and can be verified via the UI. Bitcoin's architecture emphasizes the importance of a robust and reliable infrastructure, a client-server plus P2P style subsystem for developers, and efficient tracking of UTXOs. It is crucial to differentiate between conceptual and concrete architecture to avoid unexpected dependencies that can impact the network's performance and reliability. Efficient tracking of UTXOs is essential for optimizing transaction fees and giving users greater control over their funds and privacy. Clear communication and attention to detail are critical in research and analysis, as demonstrated by our incorporation of feedback and modification of our conceptual architecture style to the client-server style. By integrating these insights to our work, we can contribute to the continued growth and development of Bitcoin and other decentralized digital currencies.